Okay, so now that we have started talking about the phase of a pulse, there is something that we need to know about the way in which we represent these pulses, especially graphically. Since the function phi of t is now the way we have defined this function and our pulse, phi of t can be anything, okay, it need not even be well behaved, as I said. All you care is that it should be sufficiently differentiable if you wish, so that you can Taylor expand it and arrive at a reasonable description. Whether you can measure it is another, measure it directly in the time domain is another question, but you always have the frequency domain to come to our rescue in such scenarios. So, if we keep those kind of questions away for the moment, or at least postpone asking them, then a graphical description of these pulses tends to be then our recourse to having a good idea of what they look like and what they are. So, the phase essentially should the phase clock, if you wish, should roll over from like minus pi to pi, or from say 0 to pi, right. So, you could say minus pi to pi, or 0 to, sorry, yeah, minus pi. If that is minus pi, this should be pi, right. But you also have a description. Oh, did I? No, I am wrong about this. I am terribly wrong about this. If it is minus pi on one side, it goes through minus pi, this is 0, and it turns over to 2 pi at the same point. So, if I subscribe to the idea that this is the 0 of pi on one side, the clock rolls over, rather the phase clock ticks if it is something changing in time, and it comes to the value 2 pi, and then it can roll over from 2 pi to 3 pi to 4 pi to 5 pi to 6 pi, multiples of 2 pi and so on. So, it is essentially the phase dial keeps say rolling over, but technically we essentially realize that ultimately all these waveforms are represented in the Fourier sense. So, we always think about the constituent sinusoidal waves, which could be even infinite in number in the case of an aperiodic say function in time, right. All sort of a continuum of frequencies within a range can have non-zero amplitudes for all of them, and we can still successfully mathematically describe them as a linear sum of sinusoids, in which case the phase essentially is also a variable that can take a value all the way from 0 to something unlimited on either side, positive or negative. But for us, in describing these pulses, we wanted to sketch the basically sketch the phase, right, and intensity and phase in one plot. When you measure these quantities, okay, think of an interference fringe, set of interference fringes. You go from dark to bright to dark to bright, right. So, if at any point I set one of these, one of the maxima or minima to be like a reference 0, then the phase from there rolls over to say from 0 to a pi to a 2 pi, yeah, 0 to pi over 2 to pi to 3 pi over 2 to 2 pi, right. So, you would go from the center of a bright fringe through a dark center of a dark fringe, and again come back to the center of a bright fringe. In all these cases, the phase would have rolled, in this case the phase would have rolled over from 0 to 2 pi. And once again, if we engage in this exercise, we would again say, okay, consider this to be 0, it goes over a 0 crossing, a minimum, a maximum, and so on and so forth. So, a measurement of any kind of this phase quantity will very well yield us with what we call the wrapped phase scenario, because there is no absolute phase scale. We can't point to one location in an interferogram and say this is a unique 0. It is there is a sense of relativity in that. This keeps rolling over. So, in the measurement and any computation, we could very well come up with a scenario where the phase goes over from a value of 0 to some value like 2 pi, and then we again set it to 0 at the point, and it may turn out that it then comes back to 2 pi, and it keeps swinging back and forth, and we particularly may not like to have such a function coming out as the result of either a numerical or even real life exercise after analysis, simply because these spiky points, the sharp points here where there is a discontinuity, like we can't take the derivative. Okay. Whereas what we are always concerned about is the phi of t function. So, in order to manage this, we would get involved in a procedure called phase unwrapping, where we essentially come up with a systematic procedure where if the phase rolls up to 2 pi and the next phase clock or whatever gets reset, we again come back, we do the necessary mechanics. If we go from a pi to minus pi, a jump occurs at one point owing to the way in which we computed it. We augment the entire thing by shifting it up first by an amount 2 pi, the next time by an amount 4 pi, the next time the discontinuity occurs 6 pi, and so on, and make this function look continuous. So, the main reason for unwrapping, one could say, is aesthetics, but also at the end of the day make this give it the semblance of a differentiable function, which is what the function should be. Whereas, we know that all the stuff here is modulo 2 pi, and so we essentially will be able to this is the left plot, the wrapped phase is probably a truer description, but then the other description also holds. But then if you really see in the complete description of the pulse, you may not do a whole lot of unwrapping, because the total field is a product of the amplitude and the phase function. Okay. As you go away in frequency from the central value to going out, the amplitude for a well behaved pulse starts to diminish, and so this whole lot of phase oscillation may or may not be of importance to us, right. Likewise, again in computations or in measurements, the following also is something of interest and importance. You may come across this in various scenarios in optics, right. So, this is the concept of phase blanking, that is, when the intensity is nearly 0, as it could be at the far wings on the outer perimeters of the spectral description of a pulse or even the temporal, the phase essentially whatever is measured is not so meaningful, right, because the amplitude factor multiplying it, weighting it essentially is 0. So, look at this description for a reminder. An electric field in its complete complex description is a point in the complex real space of real and formed by the real and imaginary axes, where the length of this 2D vector, if you wish, or phasor, is essentially the square root of the spectrum or the spectral amplitude at the frequency of interest omega I, and the phase angle is what this subtends with respect to this vector subtends with respect to the real axis, right. So, keep this description in mind, and then it is clear that if for any reason when I make a measurement, okay, let us say I do metrology of the pulse, which we have not so far in the course learnt how to do, but suppose you do, or somebody gives you a result which looks like this, it looks quite dramatic away from the phase function. Look at the phase function phi of t, in this case phi of omega or phi of t as the case may be, on the phase axis to the right vertical axis denotes this phase function, which is flat, okay, at the in the region where the Gaussian like function has appreciable amplitude, and it really becomes noisy elsewhere. Okay. This could be the result of a real world measurement, right. So, then in what do you do? This is also a part of your experimental result. So, do I present data selectively and maybe have a sense of guilt underneath that we did not do a good job of presenting the complete description, or should we show this somewhat mathematically ugly plot with fast oscillations. Okay. So, yeah, it is legal in this business to blank the face and not plot this over the entire range, but essentially leave the phase function to be a piece over here, where I show the region where the phase is unblanked and it has the amplitude of the pulse has meaningful values, okay, including maybe a reference tail which is over here as far as this is allowed to be. Whereas, at all other frequencies or times significantly away from the region where the pulse has appreciable amplitude, we simply ignore what the value of the phase is going to be, we simply blank it. Okay. So, phase blanking is inherent in these plots, in the plots that we show. So, therefore, the phase when plotted with intensity is a sort of a piecewise function. We cannot therefore extrapolate the phase function to being linear or whatever else in regions where we haven't been able to reliably measure it. So, that is something to sort of keep in mind in representing the same information. Okay. So, this is something I have been like doing in describing the phase function phi of t. So, let us see this formally for once. So, the function phi of t, which is the temporal phase function, is always best thought of in the Taylor sense, okay, because there is no unique formulation, there is no reason to presume that it should be independent of time, there is absolutely no reason to pretend that it should be linear in time or for that matter quadratic, although at some point we may say, okay, if this is a converging series, then maybe it is sufficient to take the leading order terms, the first, second and third, maybe even fourth if you so wish, depending upon the relative strengths of the Taylor coefficients phi naught, phi 1 or phi 2, where of course each successive Taylor coefficient has a physical meaning, as we have deduced. We have done this only up to the first order Taylor coefficient phi 1, which has the physical meaning of being the instantaneous frequency of the pulse, which need not be a value 0, it could also have non-zero values. Okay. Only the first few terms are typically required to describe well behaved pulses, as I was talking to you about. Okay. So, if a laser emits say 1000 pulses a second, 1 kilohertz, or 10,000 pulses a second, these terms phi 1, phi 0, phi 1, phi 2, phi 3 and phi 4 and so on and so forth, between pulse 1 and pulse 2 and pulse 3 and pulse n and pulse 1000, these need not have the same value, these need not. However, if you ask questions like what is the ratio of phi 1 to phi, just taking numerical ratios, they may not even have the same physical unit. This is frequency, phi 1 has units of frequency, phi 2 has units of frequency divided by time, which also will give it its own physical interpretation. Phi 3 is frequency divided by the square of time and so on. But then if I simply consider the numerical ratios across different pulses, it would be sufficient if the ratios turn out to be of similar magnitude. Then we can more or less say that the pulses that are coming out, all of these have a certain degree of similarity. Okay. So, the whole point nonetheless is that expanding the phase in time is not such a common practice, because it is difficult, almost virtually impossible to measure this out directly in time. Okay. Although there are ways to maybe think about this or even ways to, I mean, one can say in certain cases that yeah, we can even get a direct time measurement, such as in the case of attosecond pulses, which is really a very advanced and forefront area of direct time measurements. We would very often measure pulses in the frequency domain, aka frequencies are we more often than not do spectroscopy that is in the frequency or wavelength domain rather than chronoscopy measure direct time intervals. Clocks give us the feeling that they are direct time measurement devices, but of course, if you look underneath the cover there is actually a frequency keeper, right. Nonetheless, there is a difference between measuring time intervals and measuring frequencies, principally speaking. So, we want to sort of emphasize that. Therefore, we would in the case of the phase function often resort to a spectral phase description that is in a sense more natural to these to the description of these pulses, especially from a practitioner's perspective. Okay. So, likewise let us consider the frequency domain expansion of the Taylor series of the comparable function, which is the spectral phase function phi of omega, the frequency domain description, and we now play the same game. The first term is phi naught, it has units of phase, but this is the absolute phase. Recall now that phi naught, the absolute phase of the initial phase, is just a phase. It is not a function of omega, nor is it a function of t. So, this is actually common between the time and frequency domains. Okay. It does not matter in which domain you choose to expand your phase function in, albeit you will be measuring the spectral phase function, or we will hope that we have means to measure the spectral phase function, because it looked like, at least if you were to just take my word for it, that it is difficult if not nearly impossible to measure the temporal phase function directly. Okay. Whereas, we hope that in the spectral domain we have a way to measure the spectral phase function phi of omega either in terms of omega or lambda. Okay. So, in which case the first order Taylor term phi 1 of omega minus omega naught, or what I called delta omega earlier, becomes something of importance, and we just gave phi 1 the physical meaning that it is a group delay, right. My argument there was it is this function is units of time. Okay. But then what is the second phi of t? We now have built ourselves up to give a nice physical interpretation for phi 2 of just phi 2, not phi 2 of anything, it's phi 2 is calculated at omega is equal to omega naught, right. So, what is this? This is nothing but the derivative of d phi by d omega, the entire thing computed at omega is equal to omega naught. So, it is the rate of change of d phi by d omega, or group delay in the frequency or wavelength domain, right. Now, what is n in optics? It is refractive index, right. If n is a function of frequency or wavelength equivalently, what have we been told? There are devices which can, we can capture this by essentially again sort of Taylor expanding this dn by d omega delta omega, right. So, this variation of refractive index d omega of n, what did we call this? We are habituated to calling this the dispersion. In optics, in other branches of physics and other areas physics in physics and engineering too, right. So, this is the dispersion, d omega is the dispersion of whatever quantity whose derivative I am measuring. So, here the derivative is the derivative of group delay. So, therefore, this quantity here is called group delay dispersion, the all important group delay dispersion, which will be a very important term in very important quantity as we describe not only pulses, but we ought to now understand that the group delay and group delay dispersion, or GDD for short, okay, which of course has the units of frequency by time. If it is angular frequency, it is going to be radians per second square or femtosecond square, if this as the case may be for these ultra short pulses. What becomes important? This is a material property, much like the refractive index of the material. You may have in optics studies encountered these Selmayr coefficients for the way in which refractive index as a function of wavelength is determined, right. So, you have n naught plus something n 1 by lambda plus n 2 by lambda square. So, n 1, n 2 and so on are the Selmayr coefficients which are measured and tabulated for various materials. So, likewise GDD or group delay dispersion is a material property, and it has a lot of significance in understanding or quantifying the propagation of pulses, femtosecond pulses through a medium. Okay. So, with that we are at a good point here to bring this discussion to a close for today, and we will meet in the next lecture.